All right, it's time for the great culmination. We now have all the tools we need to solve the Black-Scholes PDE. So let me rewrite a few things just so I don't have to arrow up through a bunch of stuff. First of all, at the very end of the last video, we saw that we're going to use these two equations shortly, that when you solve the underlying dynamics under the measure Q, you are left with this formula. That is if you're at time little t, at time big T, this is the solution to the geometric Brownian motion at time little t with a drift of r. And then down here we have the same idea, so it's an equal sign. This is the solution to the geometric Brownian motion SDE from time little t to time big T under the measure QS. And recall that was basically what that means is when you have S as the choice of numeraire. If you're just watching this now, I guess I should note that there's 3 prior videos. The first one is deriving the PDE. The second is about Girsanov theorem and what it means to have a change of numeraire and Q dynamics versus P dynamics and QS dynamics versus Q and P dynamics. And the previous video showed you how to get these types of solutions to the resulting geometric Brownian motion dynamics. So let's go on to solve this one. I hope this video isn't too long, but it looks to be like it'll be the longest one. The way that I'm going to show you how to solve the Black-Scholes equation is using something called the Feynman Kac theorem. And basically what this says, I will basically lay out the idea in the same way that they do it on Wikipedia. That way you can just go check and look at their references if you want, and maybe it'll there'll be some continuity there between what you find and what I say here. So basically Feynman Kac tells us that if we have a parabolic PDE of the form du over and the little symbol I just draw is how I'm doing partial derivatives, so I'm changing from the notation that I used in my first video. Du over dt xt plus some mu xt du over dx, make that clear to be a u, plus, continue down here, 1/2 sigma squared xt over, so it's the second partial u with respect to x, minus some function v that depends on x and t, u xt, and then finally plus f x t equals 0. And importantly, this is subject to a t boundary that's u of xt is equal to some function psi of x. So looking at this, I guess first I'll tell you the result of the theorem. It's that if we have a parabolic PDE of this form, the solution can be written as a conditional expectation where u x t is equal to the q expectation. We go from t to t, e, sorry, this is going to get hard to write because there's a ton of little shit in here. Wow, it's going to prove more difficult than I thought. Come on, integral, there we go. That's from little t to z is what I'm using there. V x, and that's a tau. This notation isn't going to matter in a second. Again, I'm just trying to roll with Wikipedia's. That way you can maybe, and I'm gonna, just so I have room, obviously that's an exponential and all this is times fx subscript z, comma z, dz. I'm just going to keep like I said, the notation consistent. That way you can go check for clarity. But this will change to the notation that we are used to in a second here. And this is from little t to big T, but again, the x tau. So that's like x subscript tau. Tau d tau. Normally, so like for something x subscript tau, normally I was writing x parentheses tau. So same idea. It's not like before where I was using subscripts to denote partial derivatives. And then this is all times that psi function. Given that x and little t is equal to little x. Okay. So again, that's a lot of notation that we aren't used to. But I, again, just wrote it like that so you can go check. So the point is here I'm going to draw analogies to what we had so it all makes sense now. First things first, I'm going to use a notation. So I'm going to write the expectation of q, and then I'll do subscript t comma x. For me, that's the same thing as when you have, say, expectation under q of some stuff, and then given x, t equals x. So that's just notation that I'm going to use. And I guess another important thing is that this is all assumption under probability measure q, such that x is an Ito process driven by dx equals some mu xt dt plus sigma x t d w q, where w superscript q is a Wiener process under q. So that's Feynman Kac. Probably seems a little confusing now just because of the different notation, but I'm going to now draw the clear analogies to the Black-Scholes PDE. So I guess first things first, in Black-Scholes, obviously we have that the this function here, we don't have it in the Black-Scholes PDE. So f x t is 0. We also have the u function for us is equal to, I did f, capital F, I should say. And again, remember that was also equal to pi in our derivation. For us, if you notice this v function here, for us, that's going to be equal to the interest rate R. For us, we're doing that's a constant, so the the xt drops, and for us the psi function is like our terminal condition, our payoff function. So you know that for a call option, this is equal to the max European call option is equal to the maximum of the terminal x minus the strike, or 0. Another thing to note here is, so for us, since we have this constant of r, so when we have the function that in the notation I just wrote out, we have something like the exponential, the negative integral from little t to big T, v x subscript tau, gamma tau, d tau. This is the same thing in our case of saying e t to big T r d tau, which is just equal to e negative r big T minus little t. So that can be important to note, so we don't have to do it later. So yeah, we see that our Black-Scholes PDE thus is a great candidate for application of the Feynman Kac theorem. It might be Feynman Kac or Katz, I don't know, I'll say Feynman Kac. Mark Katz, I don't know how to actually say his name. But for our application, we thus can use the idea that such a parabolic PDE can be written in terms of a conditional expectation as thus. And again, using all these sort of analogous substitutions that apply to our particular problem, we are going to have that the option price is equal to, and again, you'll see that notation that I introduced here. So I'm going to write t comma s down here, and then a negative r t minus t phi of terminal value of s. So this is our solution written in terms of conditional expectation given the Feynman Kac theorem. So remember up here, so for us again, this function, we don't have this function, so this entire thing drops out, leaving just this portion. And for us, the idea that this, again, since v for us is just the interest rate, that part given by this whole thing, and then also for us the terminal condition psi for us is the payoff function of the option here. So that obviously again leads us to this. Now obviously this doesn't really do anything for us. You're probably thinking this doesn't look at all like the Black-Scholes solution, I know. Well, of course, because we're far from over. So again, note this payoff here. So let's rewrite this conditional expectation that we just did as such. So pi, I'm going to drop the ts to save room, equals the expectation of r t minus t, and then I'm going to write in the payoff function. Let me redo that, it doesn't look very good. Okay, and then we have max terminal stock minus k. So again, this is obviously for the standard European option. Now, what I'm going to do is break this up into two pieces. I am using an indicator function, so I'm going to say that pi can this be said to be equal to the negative r t minus t times st, the terminal stock price, times, so that is a chi symbol. I use it as an indicator function. I think some people also write like a big bold I. I think some people also write like a double one looking type symbol. But I like to use chi. Chi, so it's an indicator given that s at terminal greater than k. So we'll call that equation 1. And then obviously we have to think about the next part, which is then minus the same idea, but then obviously negative r t minus t k, and then the same idea, indicator function such that st, the terminal underlying, is greater than the strike price. So we're going to use these two equations, and again, so this came just from splitting this up and then recasting the whole max thing as simply an indicator function that simply gets activated as long as the terminal stock price exceeds the strike price. So we're going to move forward by solving these two separately. Now 2 is easier to solve than 1, so I'm actually going to start with that one, and I'll call it pi 2, and then likewise we'll do 1, and I'll write it as pi 1, and then so in the end, pi is just going to equal pi 1 plus pi 2. So moving ahead with the pi 2, so that basically starts from right here. K is unconditional, right? It's a fixed amount. So really what we have here is a cash or nothing, a binary option. And since it's unconditional, it can get moved outside of the expectation. So the point being that we can rewrite this as negative k e the negative r t minus big T minus little t times the q expectation. That make that a little more clear that it's not an x, it's chi. St is greater than k. Now, what do we have here? We simply have the expectation of this indicator function. Well, that's just the probability of this event happening, in particular the q probability. So really what we can do is rewrite this as pi 2 equals negative k e to the negative r big T minus little t times the q probability that S, the terminal stock price, is greater than the strike price. Now, this is where we need to remember what ST is, and again, that was given in the last video. And this is under, again, we are under probability measure Q. So it's going to be this formula here, the Q dynamics of S. And again, here I was using, parentheses, and now I'm just using subscripts. So S subscript T is that solution. So write it here. So we have pi 2 is equal to negative k e negative r big T minus little t times the q probability that I'm going to have to extend this down to the next line. Q probability that S at little t times exponential r minus 1/2 sigma squared t minus little t plus sigma wq t minus t. Close out the exponential, and then that is greater than okay. So all I did here was replaced ST with the solution that we had derived earlier under the measure Q. So the solution to the Q dynamics of S. All right, so if we first take logs, so I want to get rid of this exponential first. Well, first thing I would do is I would divide by both sides by ST, so moving this over here. Then I would take logs to get rid of the exponential. So first divide both sides by ST, and then take log of both sides to get rid of the exponential. And then what I would do is I would move this part over also to the other side. So after doing all that, what you would get is that pi 2 equals negative k, you get to the negative r big T minus little t times the Q probability that, and then we're going to have, so this part remained on this side, I'm not moving that, we're going to have sigma WQ T minus T, and then we're going to have the stuff that we moved over to the other side, and that's going to be the log K over S minus R minus 1 F sigma squared times T big T minus little t. So what we want to do now is to realize that this term that we've isolated here, sigma WQ T minus T, is approximately normally distributed with mean 0 and variance sigma squared T minus T. So what we would like to do is normalize this, which recall is done by something like x minus mu over sigma, where mu is obviously the mean and sigma is the square root of the variance. So in doing so, what we would get is we would get sigma WQ 0 over sigma root T minus T. So that's that. That is this normalized. So here we just have a normalized random variable. But of course we would want to do the same thing to the other side. So what really happened here? This part, right? You basically subtract the mean 0 and you divide by sigma root T minus T. So we are also going to want to do that to the other side, to this side. So subtract 0 and divide by sigma root T minus T. But I would also like to get this normalized random variable, or I should say, sorry, this normalized random variable, which I'm also going to start calling gamma. I would like to get that less than or equal to something. So how do I do that? Well, I'm going to, flip. I want to, here, see, we were still with greater than or equal to, so I'm going to flip the sign and then negate what's on that other side. So in doing all that, what you will be left with is pi 2 equals negative k e to the negative r t minus t times, do that, q probability that, again, this random variable, normalized standard random variable, gamma, is less than it's ln, and then remember I divided by this and then had to negate everything to flip the sign, so we're actually going to have s over k plus r minus 1 half sigma squared t minus t, and then divided by sigma root t minus t. Now, if you've seen the Black-Scholes solution before, this should be starting to look very familiar to you. So what do we have with this whole term? Well, we have the probability that some standard normal random variable is less than some number. Well, that's just the cumulative normal distribution function. So that's why in standard Black-Scholes this has become known as D2. And the cumulative normal distribution function n of x then becomes n of d2. Thus, this part of the equation, that is pi 2, finally becomes negative k e to the negative r t minus t times n of d2. So that is the solution to that part. So recall we split up when we wrote things in terms of indicator functions. We split them up here into equation 1, equation 2, and thus we say we move forward as pi 2 and pi 1. So that's the pi 2 part. And this is also the solution to a short binary call option, a short cash or nothing call option. So take away the negative in the front, and you have a long cash or nothing option. And you can verify that with an extremely quick Google search, or if you have something like John Hall's textbook, you can confirm it in there in the exotic options chapter as well. So we have that, but now what about 1? We still haven't solved 1. And like I said, we're doing the second because this one is a little bit trickier. So we'll call pi 1 equals, it was the Q expectation that e to the negative r t minus t s t. So the times the indicator function that the stock price ends greater than the strike price. So this one is a little problematic because of this. This is conditional now. It's not just a fixed. We can't just consider this like a cash or nothing binary where we can just take that out because it's unconditional. What we have now here is an asset or nothing call option effectively. So it's given that ST, given the terminal value of the underlying is greater than ST, we get ST, but ST is itself obviously a random variable. So how can we handle this? Well, the first thing to realize is that this term right here is also the same thing as 1 over e to the negative r t minus t, which is the same thing as just 1 over, say, a bond at 19. Yep, want that. And sorry, I moved this down so the negative is gone. Furthermore, understand that we really have an implicit over here. We could say that this is implicitly, so because we're under Q, we have the bank account as the numeraire. So implicitly there's a b of little t over here. It's just that, well, what is that equal to? B at little t can be thought as being e to the r little t minus little t. Well, that's just 0, so this just equals 1. So implicitly that's over there. So why is it important to think about it like that? Where you basically, think about this being gone, and so it's this whole thing divided by bt, and then this part here again, divided by b of little t. Well, what we're going to do here is we're going to change numeraire. Right now we're under the measure Q. Let's change to QS. Why does that help? Well, why it helps is that we would then have pi 2 over s of little t equals EQS expectation TS times ST indicator that the terminal underlying is greater than K, and then all this over, forgive the brackets, they're not just in the, all this over ST. Well, the indicator function is this is just multiplication. So this does cancel, like, I mean, the regular rules of algebra work there. So that cancels. So that's good. Because that ST being inside the expectation was, obviously there's ways to solve that. I personally find them extremely messy and complicated, and I like this way better. So getting that ST out of the expectation, that random variable, is fantastic. So what we have now is we have, and I'm also going to move, you know what, big problem here. We have moved on to pi 1. What am I doing? I didn't make that mistake in the other test, did I? I did, okay. So pi 1 is now, and I'm going to, moving the ST numerator over here to the other side. So S little t times the QS expectation, that, make that clear, the indicator that delta okay, so this looks familiar. Remember last time we said if we just get the expectation of an indicator function, it simply turns into a probability of this event happening. So we rewrite this, pi 1 equals s a little t times the QS probability that the underlying matures at a higher value than the strike price. So this we saw before with one difference. Up here we had the same idea but with a Q probability. This is just the QS probability. Well, what the hell does that mean? Well, it means that the dynamics of S are now under QS. And if you remember from the last video, we solved what the dynamics look like under the measure QS. We saw actually in the second video, the Gersinoff video about change of measures, we saw what the dynamics were. In the last video, we saw what the solution ends up being. And I'll write it here, just so I don't have to go back up. So equals S. No, excuse me. Oh yeah, sorry. It's D times exponential of R, and it becomes plus 1/2 because we have a transformation kernel of sigma squared. So basically before we had R minus 1/2 sigma squared, but we need to add a kernel of sigma squared. Or sorry, not a kernel. The kernel of sigma. But we end up adding sigma squared to negative 1/2 sigma squared, and this gets us plus 1/2 sigma squared t minus t plus, but of course now we are under QS. So that is your solution. 2ST. But with that, we're going to follow the same idea in that here we will just pop that into here, and start solving. So let's rewrite this as pi 1 equals s little t times the q. So these, again, it's like thinking of a Wiener process under q versus qs versus p. This qs, it's denoting the probability. It's just probability. So don't think like, well, do I have to completely change my notion of what probability means? Well, no. The stuff we're doing inside of it is taking care of the changes that need to be made to move to that measure. So think of it like it's just like flipping a coin. Probability is 1/2. Basically, what we've done is we've changed the coin. We didn't have the right coin at the beginning. It wasn't giving us 1/2. So what we did was we changed it so that we could think of it in those same kind of terms. Maybe that's a completely wrong, bad way to think about it. But with this, we have QS that we have S T times E P plus 1 half sigma squared T minus T plus sigma dWQ. Sorry, QS that's greater than K. So again, same idea here. What I would do is I would divide both sides by S. Then I would also take logs of both sides to get rid of the exponential. And then I would also move this remaining term then to the other side, leaving the following. S a little t times probability that sigma, sorry, you know what? These aren't differentials now. We solved the equation. Come on. Okay. Okay. W QS is greater than. So we're going to have ln K over S. And then minus, I'm going to write it down here. So again, first thing I'm going to do is normalize this random variable. And in doing so, I have to do the same operations to this other side. So it's the same as before, so that sigma WQS T minus T is the same idea. It's normally distributed with mean 0 and variance sigma squared T minus T. So you get the same normalization where you effectively just divide by sigma root T minus T. And then again, I'd like to get, I'm going to again call that some random variable gamma, and I'd like to get that to be less than the other side. So I'm going to flip the sign and therefore negate the other side, leaving that pi 1 is equal to S a little t times QS probability that some standard normal random variable gamma is less than ln S over K plus finish down here, plus r plus 1/2 sigma squared t minus t, and then this, you know what, I should my little pen would decide to work. I should write all this in one line so that dividing doesn't get confusing. Ln s over k plus r plus 1/2 sigma squared. That's the result of being under QS. Sigma root t minus t. So the difference from before, when we had that thing that we decided to call ND2, it's really only this. Because we were under the Q dynamics there, and now under QS, it becomes r plus 1/2 sigma squared. But obviously they're different, and therefore we need to name this something else. Actually, it's just this. So we have the QS, basically the probability that some standard normal random variable gamma is less than something. So again, we have a cumulative normal distribution function acting on the inside here. And normally this is called then D1 as compared to D2. So we have that, you know, including, we have n of D1 is this entire thing. And remembering that we have this time multiplied by st rather than k, basically the discounted k, we get that pi 1 equals s little t times n d1. Okay, well look at that. Recall that we had pi 2 was equal to, and also just to note, this then, remember I told you that, let me write it first, e negative r t minus t n d2, that this was equal to a short cash or nothing call. So basically just this part without the negative in front is a cash or nothing call, and because it's negative, it's it's a short cash or nothing call. This here is a long asset or nothing binary, and you can confirm that too. So, but the bigger, the more important point is that the way we split it up in the beginning, we said that pi is equal to, that is the full price of the option is equal to the sum of those two. Well, what do you know? That means that pi must be equal to st n of d1 minus k e to the negative rt minus t times n of d2. And that there is the Black-Scholes option price. It's the solution to the PDE we saw 4 videos ago. And you can obviously check that to confirm, but that is a very, very widely known result. And again, another cool way to think about it, now that we went through this, so the Black-Scholes is basically a long asset or nothing binary and a short cash or nothing binary. So there is the way that I know to move from 4 videos ago, simply deriving the Black-Scholes PDE up to solving it using the Girsanov theorem that was in the second video, and you know, the concept of change of measure or change of numeraire. And here we saw the solving it via the Feynman Kac theorem, which basically says that you can solve a parabolic PDE by casting it as a conditional expectation under some appropriate measure Q.